Okay, now we're good. Okay, so yesterday, sorry, wrong place. There we go. Yesterday, we started taking a look at graphs of functions and talking about some properties related to symmetry. Is this about where we left off? I think, yeah, I think I pretty much got to the same place in all three. We took a look at y equals x squared as a function. So the function that takes whatever number you want to give it as input and squares it, right? Just multiplies it by itself. Its graph looks like this. We'll just graph that with a calculator or a computer. Its domain and range, all real numbers, and then the range is just 0 to infinity. Again, domain, we're talking left, right, or x values. So the fact that one of those ends points to the left and the other one points to the right, and we don't skip over anything, that's what tells me that the domain is all the real numbers. The range 0 to infinity, well, this has a lowest point. We're talking about y values, we talk about range. So this has a lowest point at 0, and then ends that are pointing up. That's in the direction of positive infinity. And that gave you some time, and we kind of talked through these points that are marked. The thing to notice is that everybody's kind of got a buddy, right? They match up, and the way that they match up, for example, these two, is that the x values are opposite in sign, but the way we want to think about sign is just direction, right? So in a number line sense or a graphical sense, 2 and -2 are the same distance out, just in opposite directions. But what happens with the y values is that they're identical, they're the same, right? So these 2 points that are opposite each other relative to the y-axis are at the same height. And that happens for everything. We call that y-axis symmetry. So the y-axis, the vertical, this one, acts like the middle of this graph, and it basically acts like a mirror. Or if I hold that line still and flip it over, then I get a thing that's identical, right? That's what y-axis symmetry means. In the algebra, right, in the sort of symbolic version of this, if I replace x with -x and then simplify, I get back the original function. Right, it's identical to the thing that we started with. The negative cancels because there's 2 of them in a square, and you get x squared, which is what we started with. That means the same thing, right? That's algebra saying, oh, there's y-axis symmetry going on. We call those even functions. So anything that's got y-axis symmetry like that is an even function. Here's another example of something that's got that same kind of symmetry. If you've done the trig before, this is the cosine function. If you haven't, that's okay too. It's a graph that has y-axis symmetry. If I hold this line still and flip it over, or if I fold it over on that line, then the 2 sides line up, right? They're identical. That's another even function. Okay, and then I think I told you to go and do this, or attempt this. So we're going to do the same thing, but looking at the cubic function now, y equals x cubed, hang on. Y equals x cubed. I want to do all the same kind of stuff. Again, the domain and range thing, we want that to be kind of getting to a place where I can just like look at a thing and do it and not really have to think about it that much. So let's start there. Domain and range for this. Domain, we want the x values. So either what's going on left and right, or again, if you want to think about it as sort of, smashing the thing down onto the x-axis, like where does it fall? Where does it land? What do we think? Yeah. Which direction is this pointing? Down and left, right? Like if I'm just looking at the picture and I'm putting, the little like arrowhead thing on it, that's going down into the left. Domain, the part I care about is not the down so much, but the left, right? Left is the direction of negative infinity, right? That's where you put it on the number line. The other end is pointing, yes, up, but also right. Okay, I got one end pointing left, I got one end pointing right. There's no gaps or breaks or stuff left out or whatever. That's everything. It's covering the whole real line. So that's negative infinity to infinity for the domain. What about the range? Same thing, we're talking y values now, so now I care about the down and the up, but same idea, it's gonna be all real numbers. Okay, now the noticing stuff part. What do you notice about what's going on here? For example, 1 point on the graph. Hang on, let me just draw this on the board real quick. I forgot I have my graph with all the points already marked pulled up. Say 2, 8, and -2, -8. Those are 2 points that this graph goes through. Yeah, sir.
I was just gonna say, I don't think I got that paper that y'all are on right now.
Okay, sorry. The same thing, maybe.
Is this the one that you're on?
Oh, yeah, 2.1. Yeah, yeah.
I do have, I just was confused maybe.
Okay, well, the graph that was on there, I pasted that in yesterday. That QR code at the top, that'll pull it up.
Okay.
Yeah, you just scan that. Okay, so if I look at, again, like a pair of points that go together, right? Now, what do we notice about them? How they're related, how they're similar, how they're different? They're opposite. Can you be more specific? The x values are opposite, right? Same number, but opposite sign. And also, the y coordinates are opposite, right? So the square was one of the two, right? I had like 2, 4 and -2, 4. One of them was opposite, the other is the same. Here it's both of them. So, and that happens for everything, right? It's every point over here has got a buddy over here that's, opposite in sort of both sides. How can we describe that then? How can we describe the like symmetry or the like pattern there? What acts like the middle or the sort of mirror here? The origin, yeah. So for example, like 2, 8 and -2, 8 or -2, -8, those kind of go together, right? Well, that's if I'm the y-axis, that's a point over here and a point over here. They're at the same like distance, but they're in opposite directions, right? One's up here, one's down here. And if I looked at all of them, the same kind of thing would happen, right? That it flips both ways. You can either think about that as a like reflection flipping over thing, but to reflect and flip over, you would have to flip this way over the y-axis and then also flip it upside down. That kind of makes sense. Like keep track of one piece. This, if I flip over the y-axis, I get this, right? Well, that's not where I want it to be. I want it to be down here, so I got to flip it upside down too. Okay, so we can either flip and flip again. That's fine. Another way you can think about that though is to hold that point still, right? The origin, the one that's on the y-axis and the x-axis, that's the only point that's on both. Hold that still and spin it upside down. So if you have that graph in front of you, if I look at this and hold the origin still, imagine holding the origin still and spin the whole thing upside down, which you can do by spinning your head upside down because I can't turn the screen. I guess if you have it on your phone or whatever, you can just turn your phone upside down. Not look like an idiot, but turn your head upside down. And if you get the same thing, that's origin symmetry. That's what's going on here. So they are symmetric about the origin. And the origin always just means the point 0, 0. Let's call it the origin because it sounds cool. Okay. What about what the algebra is going to look like for this? G of x is this cubic function. What does g of -x look like? If I replace everywhere there's an x, I put a -x in. And then look for anything we can do to simplify or clean that up. What's that going to look like? Cubing means take 3 of them and multiply them together, right? So -x times -x, what happens to the signs? They cancel, but then there's still one left, right? So -x comma, long pause, all together cubed is going to be the same thing as negative x cubed, right? There's still 3 copies of x sitting there, but the signs cancel in pairs and there's 1 left over. So it's negative x cubed. Okay. Now I want to do the same thing that we did with the other one and kind of compare that back to where we started. Here's the original function. Here's what we just found. How would we describe those? Well, they're definitely not the same, right? That's what happened with the other one. X cubed and negative x cubed. The difference is the negative sign, right? What does the negative sign do though? We're thinking like number line, like where you are, position kind of thing still. So if I talk about, I don't know, on a number line, 1 and negative 1. They're the same number, so they're the same distance, but in opposite directions, right? Okay, same thing here. The x cubed part, that's just some number, right? Don't get hung up on that. That one's positive, this one's negative. I'm talking about a function value, so we mean y, so that means it's opposite both ways, right? It's opposite in the x and the y. That's the same thing. That's another way of saying this, symmetry about the origin. That's what symmetry about the origin looks like symbolically or in the like algebra, right? That's what's going on. That's what that tells me. So those are opposite in sign. Why am I writing with a highlighter? Opposite. Which again means the same thing as origin symmetry. And if the other thing was called an even function, the logical choice is that this is an odd function. Odd functions, odd symmetry is a little bit, weirder, a little bit harder to see maybe at first. Here's another picture of an odd function. If I hold that still at the origin, right? Like I pin my paper to the table right there at the origin and spin it upside down, or reflect and reflect again. You can think about it that way if you want to. Then we get the exact same thing back, right? Again, forgiving my drawing, but these are the same height. These happen in the same places. Those are going in opposite directions. That's the idea, right? That's what origin symmetry looks like. Again, with both of these, it's important that we're talking about y-axis symmetry. It's got to be the y-axis that acts like the middle, that acts like the mirror, right? For an even function. Origin symmetry, it's got to be the origin. It has to be 0, 0 that acts like the middle to be an odd function. So if I took this same thing and drew it over here, that's not odd anymore because it's in the wrong place. That makes sense? Even though it's the same shape, because it's in a different spot, if I hold this still and flip it upside down, I don't get the same thing anymore. I get a similar shape, but in a different spot, right? That part's important. Okay, so where'd my pencil go? Here we go. Quick recap. Even functions. All even functions have y-axis symmetry. All functions with y-axis symmetry are even, right? Those things are synonyms. They mean the same thing. They kind of give you a different perspective on it, but they tell you the same information. And for any even function, if I flip the sign on the input, on the x value, what that does is a y-axis reflection. We'll look some more at that next week. But if I flip the sign on the thing going in and get the same result back, like all the negatives go away somehow, they cancel out, whatever, I get back a thing that's identical to what we started with. That means that it's an even function. Odd functions. Well, same idea. All odd functions have origin symmetry. All functions that have origin symmetry are odd. And the way that works out in the algebra and like the symbolic or analytic sense is that you get things that are opposite in sign. If I flip the sign on the thing going in, the input, then what ends up happening is it's the same as if you just sort of multiplied the whole function by a negative, like threw a big set of parentheses around it and multiply by -1. Because again, what that's doing is, sending something from like quadrant 1 over and then down, right, to the sort of opposite diagonally placed. Okay. Does anybody have any questions about any of that so far? Okay. Obviously, this is, different than like doing it on your own, right? So let me walk you through the stuff on the back. We're pretty much going to spend the rest of today just working problems. So on the back here, there's 3 big problems with multiple parts. But example 3, what I want you to do is take these 6 functions and look at their graphs. So grab your calculator. If you want to do it on a phone or a laptop or whatever, Desmos is my go-to graphing calculator. That's what all my graphs are made in and stuff, but it's free. You can just use it. You just type stuff in. Graph each of these 6 things, separately, right? You want to look at them one at a time. And what you're trying to decide is if they have symmetry with respect to the y-axis or with respect to the origin or neither, right? There's the third option. And then if they have the, correct kind of symmetry, what does that tell you about whether the function is even or odd or neither? Y-axis symmetry always means even, origin symmetry always means odd, neither means neither, right? That it's not either of those things. 4, I want you to draw a graph that's symmetric with respect to the x-axis. We haven't talked about that at all. We're going to figure out why. So draw a graph that's symmetric with respect to the x-axis, and then think a little bit about, what that means, what that would mean, why that's in a different place, right? Why we haven't talked about that so far. And then the last problem there, example 5, again, there's 6 of these that you're going to do, separately. But you want to determine, or I want you to, you may not want to, I guess, I don't know, but determine analytically, that's symbolically by like working out the algebra. So find f of -x, whether each function is even or odd or neither. So that's where you're actually going to plug -x in, work things out, see what you get, and then decide, okay, what does this say? How does this compare to the original function? And what does that mean about the symmetry, the parity, so on? These, of course, like you can look at a graph too if you want to like check your answer, but this is a place, and we'll see this some more through the semester too, where we got to do a couple things at once, right? We need to be figuring out how to think critically and how to problem solve, but we've also got to build some algebra skills too, right? So partly this is here for that reason. So this is a place where I want you to actually plug the thing in, simplify, see what you get, and then use that to decide what's going on. Okay. We've got, about 25 or more minutes left. So I'm going to give you guys, 10 minutes or so to kind of work with each other, get into groups of 3 or 4, talk to each other, see what you agree or disagree, or, somebody else's take on how something works. So work together. I'll float around a little bit, and then, in 10 minutes or so, I'll probably bring us all kind of back together to talk about things for a minute, and then we'll, rinse and repeat. So y'all work, and we will reconvene in a few minutes. Okay, let's take a look at those graphs so far on the first problem, which is not 1, 3, I don't know, whatever, the thing that you're doing right at the top of the page. Here's the graph for part A. What do we think? Even, odd, neither? Neither, right? But sort of subtly neither, right? This looks a lot like x squared, which is even, but what makes this neither instead of even? It's off center, right? It's still kind of got its own symmetry. I can imagine how I could pick that graph up and fold it in half and things would line up nicely and right, have that same kind of thing, but it's not the y-axis that acts like the mirror, right? Even in odd functions have some important properties that we'll, see some of later. You guys will go on to pre-calc calculus, you'll see some of those, come up there as well. There's a reason we talk about them, but it's a very specific thing, right? It's symmetry about the y-axis. Well, here's the y-axis. That's not the middle of that graph, right? Odd would mean origin symmetry, which is the turn it upside down thing. That's not happening either, so this is neither. How about that one? Also neither. With sort of similar comments, right? It's almost odd, but not quite in the right place. Right? That looks a lot like the thing I drew as an example of an odd function, but the middle is not quite where it ought to be, right? So it's neither. C, odd with origin symmetry. E, even. Next one. It's also even. You may have noticed or felt as you're going through them, like the first four are just polynomials. They don't really look all that bad when you look at the like formula, right? The symbolic version of the function. This one, square root of x squared plus 1, that's kind of like feels worse, right? There's a lot more going on there, but I don't really care right now because all I'm looking for is like the properties of the graph, right? I don't really need to really understand what that function is going to do or how it's going to work, but the graph is y-axis symmetric. That means it's even. Same thing for f, right? This one even looks weird. The last one didn't look all that weird. This one's weird. It's in two separate pieces. It's got weird stuff going on. It doesn't go through the origin, doesn't go through the y-axis at all, actually, which is different than all the others, but does it have any of the kind of symmetry we've been talking about? Yeah, right? If I put a pin in at the origin and spin it upside down, I get the same thing. Even though it doesn't pass through the origin, even though it doesn't hit the y-axis at all, it does have origin symmetry. If I look at it upside down, it looks identical. That's origin symmetry, which means it's an odd function. And I wrote those in a different order than all the others, but whatever, it's fine. Okay, everybody feel, more or less okay about that? Okay, obviously, doing things when we're all together in the room is a little bit different than, when you go home and do your homework. But so if that changes, of course, just, let me know or bring it back up. But, okay, how about a graph that's symmetric with respect to the x-axis? X-axis is this one, right? That's the horizontal. So, I just want the top half to look like the bottom half, but mirrored, right? Okay, so what about something like that? Something like that. Forget my drawing, but you see what I'm going for, right? Okay, that's symmetric with the x, with respect to the x, right? The x acts like the mirror. But what's different about it? Is it a function? Why not? No. Yeah, just about anywhere I would put a vertical line here, which again represents its x value. It would hit that graph twice, right? That means one x value, one input going to two y values. That's the function definition, right? That doesn't work. So because of what happens right there, for example, this is not a function. We talked about even functions, odd functions. We mostly care about functions. This one's not. Okay, well, maybe that's got something to do with why we haven't talked about it yet. Maybe it's just I drew the wrong one, right? Draw a different thing that's y-axis symmetric. Still no, right? Still not a function. Still not going to pass a vertical line test. Can I ever, is it just that I'm still just drawing the wrong one? Can I ever draw a thing that's got x-axis symmetry, but there's a function?
Maybe with X and Y axis symmetry.
Well, if it's got x and y, then it's odd, right? So if it's both of those at the same time, that's really origin symmetry, right? So no, right? And it kind of goes back to the whole, like what symmetry means even, right? Think about the way that we kind of worked through stuff yesterday and at the beginning of class today. The way we recognized the symmetry was by, looking at a point and finding its buddy somewhere, right? Well, if those are across the x-axis from each other, that automatically means it's not a function. So it can't happen, right? There's no way to make that work. Because there's no way to make that work, and because that means it's not a function, we kind of don't care about it as much, which is why it, didn't come up in the stuff that we've done already. Okay. All right. Now this, again, doing it analytically or symbolically or working through the algebra, again, is going to have sort of a different feel to it. And what we want to do is find f of negative x. And once we find it and simplify it and clean it up and whatever, we're going to compare it back to the original function and see if it's the same or different and how and what that tells us. So first we got to actually find it though. That's the algebra skills part, right? So I want to take this function, anywhere there's an x, I want to replace it with its opposite. So with negative x. So what does that look like? So I got the big set of absolute value bars on the outside, right? 5 times negative x, and the parentheses tell me that I'm treating it like it's one thing, right? It's negative times x, that's important. Okay, then we're going to simplify that. 5 times negative x, well, I could also write that as negative 5x, right? It's an absolute value. We're going to talk a lot more about what absolute value works like in the context of a function or how it works in a couple of weeks. But for now, what you definitely know about absolute value coming in is that it tells you about distance on a number line, right? So the absolute value of 2 is 2. The absolute value of negative 2 is also 2, right? It makes negative things, positive again. What I want to do here to simplify this down further is think of 5 times x as one thing, right? If I take its absolute value, then what that's going to do is give me the same thing as the absolute value of 5x. How do those things compare? They're the same. What does that tell us? That it's an even function. If those are the same, what that's saying is that, think the absolute value distance thing again. If I look at a point over here and its opposite, which would be a point over here, I get the same thing back from the function. I get the same y value then. That's telling me that there's y-axis symmetry happening, which means it's an even function. Okay. Has everyone had a chance to look at the one in part B? X to the 5th minus 2x cubed? Yeah, okay, somebody walk me through it. Same approach. We're going to find f of negative x. So first do the plugging in part, the substitution, right? Where there's an x, replace it with negative x. What does that look like here? Negative x to the 5th power minus 2, and then in place of this x, I'm going to put negative x again. Now it's got a cube on it. Okay. Now, work on simplifying. What can we do here? Negative x to the fifth. What about it? Becomes, so negative x, comma, long pause, whole thing, raised to the fifth becomes negative x to the fifth, right? We get to move the stress, the emphasis, because fifth means 5 copies of them. So what happens to the negatives? They cancel in pairs, right? Negative times a negative is positive, but then there's one left over. So overall, that's going to be negative. And then there's x times x times x times x times x. So that's that. And then the same thing happens here, right? Negative x all cubed is going to be the negative of x cubed. So ultimately what that ends up doing is flipping the sign in the middle there, right? It becomes plus 2x cubed. It's minus 2, you cube the thing, that was negative, the negatives are going to cancel and become plus 2x cubed. So this and this are, well, they're not the same, right? And if they're not the same, what does that tell us? It's not even. Okay. Are they exactly opposite in terms of the sign?
Yes.
Yes. This was positive, now it's negative. This was negative, now it's positive. Those are opposite in sign. Which means that this is origin symmetric, which means that it's an odd function. Okay. Let's get out of hand there. I heard, as I was walking around, a couple of people saying things about like the powers and the exponents and stuff, and if they're even or odd. When it's this kind of thing, a polynomial where it's just like powers of x sort of added together, subtracted. To be odd, they've all got to be odd. To be even, they've all got to be even. If there's stuff mixed in, you'll see that it ends up being neither. But be really careful about that. And the reason I mentioned that is because let's take a look at what happens on like the last one real quick. I got a couple minutes. F of x is x cubed times the square root of x squared plus 1. So if the only thing I'm looking at is the powers that are in there, right? What I see is a cube, which is odd, and a square, which is even. And if all I'm doing is basing on that, I'm going to say it's neither, right? Because one's odd and one's even, and those don't mix. But let's actually work it out. I'm going to replace all the x's with its opposite. And then see what happens. So what happens when I go to clean that up? I get negative x cubed on the outside. And then x squared plus 1 on the inside, right, under the radical. Okay, well, if I'm comparing these two things, they're definitely not the same, right? For sure, it's not an even function because they're not the same. One of them's got that negative sign out in front, the other one doesn't. Is it odd? Are they opposite in sign? Not all of them, right? There's a plus that's still a plus, right? Is what you're saying when you say not all of them, right? Okay, let's look at the graph though. Y equals x cubed square root x squared plus 1. Is it odd? Yeah. Yeah, it's origin symmetric. It's an odd function. So this is why I don't want us to lean on just the powers being even or just the powers being odd or whatever. That is opposite in sign from the original thing. When we talk about being opposite in sign, what we really mean is if I took the original expression and slapped a big set of parentheses around it and threw a negative sign there, multiplied it by a negative, This is all one piece, right? The way that square roots and fractions and stuff like that work is that they act like a grouping symbol. You treat that thing like it's in parentheses. So this is one thing. And this is connected to it by what operation happens there, connecting the executes and the square root. That's multiplication, right? So they're connected by multiplication. That means it's still all one big thing. Well, the way you take one big thing and make it opposite in sign, the way we've been talking about, is you just throw a negative sign on the outside of it, right? I wouldn't distribute that negative into the square root or anything. I would just do that, which is exactly what we have. So this is an odd function. It has origin symmetry. We just have to make sure that we are careful about our like perception, our expectation of what it means to be opposite in sign, right? It's not necessarily that every plus becomes a minus and vice versa. If it's just a bunch of separate things added together, then that's what that means. But this is all one thing, right? These are all connected by multiplication. And again, that square root is like a grouping symbol. So the opposite thing looks different than you expect sometimes, okay? That kind of makes sense? Okay, now again, you going home and doing